Hey everyone, and welcome to Unit 3 on free body diagrams and 2D equilibrium. Today, what we're going to talk about is two particular things. One, we're going to introduce what free body diagrams are all about, learn how to kind of use them, and why they are applicable, particularly in ENES 102. The second thing we're going to talk about is the idea of 2D equilibrium. Now, using the sum of the forces will help you solve static problems, particularly in this class and in the real world. Let's get started. Alright everyone, just like usual, I want to start today's lecture off with a question to you. I'm here at the beautiful Physical Sciences Complex building at the University of Maryland, and I figured there's no better place to start our lecture off than here, because our opening question today is, what are Newton's laws? As an engineering student, you should 100% know what Newton's laws are. You should have pretty much a pocket-size booklet of them inside of your wallet, just in case you're ever in a tricky situation out in the real world and you might need to recall what they are. So, pause your video and think through what Newton's laws are, and then we're going to review them and explain how they apply to ENES 102. What are Newton's laws? Let's review. Newton's first law says that an object in motion will stay in motion unless acted upon by an outside force. Or similarly, an object at rest will stay at rest unless acted upon by an outside force. This is commonly referred to as the law of inertia, which I'm sure we've all experienced ourselves when we're nice at rest in our beds and we have to wake up for an 8 a.m. class. We need a good old kick or force to get us going. For me, that's a nice good old cup of coffee. Newton's second law says that F equals ma. That's pretty much what usually everyone says, but what that really means is that if you have a net force on an object with a mass, it will cause that object to accelerate. Now, the good news for us is that this is ENES 102, and all the objects in this class are static, meaning there's no motions. So, the acceleration in our class will always be 0. Whew! Thank goodness for that. That makes our lives a lot simpler. You'll learn about moving objects in ENES 220 and in ENES 221 later on in your academic career. Now, Newton's third law, which is probably the most important specifically to ENES 102, is that for every action, there is always an equal and opposite reaction. And that always occurs between two objects. So essentially, this is going to be the very basis for which we develop free body diagrams, as we draw the forces in every system and how they interrelate to each other. Now, one quick thing before we move on I want to ask you is, if Newton's third law is really true, and any two times objects interact, the forces are equal and opposite, how is it that you can take a hammer and hit a nail, and drive that nail into a piece of wood? Because if you really think about it, if the hammer and the nail are meeting and the forces are opposite, wouldn't they just cancel out? Think about that question for a second, and we'll go over the answer and begin to further delve into free body diagrams and Newton's third law and how it relates to this class. Did you have a chance to think about it? Essentially what's happening is that when you look at the difference between the hammer and the nail and why the hammer is able to drive that nail in, while the forces in fact are equal, that the force of the hammer on the nail does equal the force that the nail applies to the hammer, Newton's second law says that ma is equal to the net force. So if we set the mass of the hammer times the acceleration of the hammer equal to the mass of the nail times the acceleration of the nail, what we can see is that the difference is that the mass of the hammer is substantially greater than the mass of the nail. And as a result, the accelerations are going to be commensurate with that difference. So the nail being smaller is going to have a much higher acceleration than the acceleration of the hammer, which is going to be much lower. Now, an example of this in the real world, in addition to the hammer and the nail, is anytime you have a collision between two objects. One is in football. When you got a big guy hits a small guy, the big guy's always going to win. And another pretty funny example of this that many of you have possibly seen in YouTube videos is when a big person is holding a medicine ball and they collide with a small person with a medicine ball. The results are usually pretty catastrophic, but in some ways also pretty funny too. Let's check it out. Joking aside, why do free body diagrams matter, particularly in the context of this class? Well, it's my guess that each and every single one of you wants to get a super A+ in this class and get 100. And as I told you already, it's my goal that all of you get a 100. So free body diagrams are going to be a component of pretty much every assignment and every exam. On exams, they're usually the first part of every problem and are going to add up to be maybe 20 to 30% of your exam grades. So if you want to get that high score, you're going to need to do a really good job drawing free body diagrams. The second reason why they're really important is looking at the engineering design process. As an engineer, your first and most important step is to define the problem. And by drawing a free body diagram, it helps you model the system that you're trying to solve. So essentially what it's going to do is it's going to help you visualize what's going on in that problem. And as a result, you're not going to walk through it blind, like in that super awesome movie that you can see below, but it's going to help you solve the problem, because for an object to be at rest, every single force in your problem is going to have another force be able to balance it out. Now that could be involved with force components. A force might have an X and a Y component, and those components must always be canceled out by other forces in the system. So very quickly, if you start a free body diagram and you draw only one force, you should realize right away that you've made a mistake, because something has to be there to cancel that force out. Ultimately, free body diagrams are very important because they provide you a map in order to know how to solve the problem. Usually, very quickly, you can look at your free body diagram and figure out what do you not know and what you do know. And by balancing those two things, you can figure out where you need to go next in order to solve the problem. So how do you apply this in ENES 102? When you're drawing free body diagrams, always follow these steps that I'm going to outline shown below. We're going to take a very straightforward example of a box just sitting on the ground. As you can see, step number one is to always draw the picture as it is in the real world or as in the problem statement. Here we just have a box and it's resting on a blue line, which we're essentially saying is the ground. The second step that we want to follow in a free body diagram is to indicate our XY axes. That way we have kind of a reference point to use for the rest of the problem, so we know how to break up our forces into the X and Y components. Our third step in a free body diagram is to account for all of the forces acting on the body of interest. So this is really important, because when we draw those forces, we want to draw them where they are acting on the actual shape. In this particular case, we've got the weight mg of the box acting from its center of mass going straight down. The second thing we would be the normal force moving up to counteract that force. Here what you can see is that our free body diagram at least conceptually makes sense, because we've got two possible forces that can balance each other out. Had we only had mg on a free body diagram, we should have quickly realized that this system can't be at rest, because the net force would be one force, and that would indicate our object was moving. There must be a second force in ENES 102 to cancel that out. And last but not least, in a free body diagram, this is going to be particularly important as we move forward in the class, is you always want to draw applicable dimensions. You want to draw the dimensions from the edges of your system to where forces are acting and show the overall dimensions of the system in question. Here's a big no-no for free body diagrams. A lot of time in physics, you might see something that looks like what you see below. A dot with an arrow down and an arrow up. Definitely don't do that, because what's going to happen is eventually you're going to lose all this information. When I was telling you before that forces can rotate and spin and all of these things, if you've got only a single dot, then you're going to lose information. You need to always draw the shape as it is and draw those forces where they're actually acting. As I was saying in the Forces and Moments lecture, if you apply force through the center of mass, an object is just going to move in a linear sense. But if you apply that force above the center of mass, then that might actually cause the object to tip. Let's look at two forces that are going to be fundamental to the class and behave in a particularly special way on free body diagrams. Those two forces are the normal force, which, what a great name, and the force of friction. So what we have here is we've got a box on a ramp that's inclined at some angle theta. The first force we would draw in this free body diagram would be the weight of the box acting straight down. And what we can see with the dotted blue line is that the angle of the ramp theta is the same at which the angle of the weight is inclined relative to the ramp as well. And I'll show you this more in the next slide, how this works. As we can see, we've got only one force, so our object would be out of balance. We need at least another force. The force that we need is the normal force, which is going to be the force of the surface acting onto the box. Now, it's very important to realize that the normal force always acts perpendicular to the surface onto the object that's touching it. Okay? The next force, as you can realize, because the normal force would only cancel out the weight going into the ramp, in order for this box to be at rest, we would also need another force directed along the ramp, which in this case would be the force of friction. It's important to recognize that the force of friction can only ever act parallel to a surface. So it'll act in between the junction of the box and the ramp itself. For those of you that don't quite believe me when I say that the incline of the weight is equal to the incline of the ramp, here's a really useful illustration for you. What you can see is the yellow dotted line represents the ramp, and the blue line represents the weight. Now, if I essentially rotate the XY axes by making these other dotted yellow lines, and I include the angles, what you can see is because I've rotated the XY axes by a certain angle, the angle in between each of those dotted yellow lines and the black regular XY axes, they're all shown in blue. Those all have to be the same. If that's true, if our two yellow lines that are parallel, the one going through the box and the one going through the center of the XY axes, we can essentially showcase that the angle there has to be the blue angle, which you can see the two lower angles match. That's how we know that the angle of the ramp is equal to that angle in the free body diagram for the weight. Another very useful tool in this class and in all of your engineering classes is this methodology called extreme case reasoning. What this more or less means is if you're ever confused by a drawing or a particular situation, you just need to think of the absolute most ridiculous version of that problem. So in this case, what I've done is I'm showing you a ramp with essentially an angle of 0. By then drawing the free body diagram of the block and drawing the weight down and then drawing the force parallel to the ramp and perpendicular, what you can see fairly quickly is that the two small angles match up. This allows you to visualize the problem better and to more quickly realize that the two smaller angles match and verify your free body diagram. Now what we'll do is we'll look at an example of a free body diagram and have you take a minute to practice drawing forces that are helping to keep this book and this person at rest. You've essentially learned all the things that we just talked about, the normal force, the force of friction, and the weight, and how to draw forces. So what I want you to do right now, just take a minute, draw this picture on your paper, and try and figure out what are the forces acting on the book. So isolate the book in and of itself, draw that, and then isolate the person and draw the forces acting on that person. I'll give you a minute or so to work on this problem and kind of draw out what you think is going on, and then we'll go over it. Alright, let's look at the book in question. When we draw a free body diagram of the book, we would get the following shown below. What essentially we're drawing here is the weight of the book acting straight down. We knew that that was the case. What we also have to do is we have to account for Newton's third law, which says that anything the book is contacting, there's going to be forces in between those two systems. So the book is contacting the wall and it's contacting the person. If you were the book, always think about how you would feel in the system. So if you were the book, you feel the person pushing you to the right, and you feel the wall pushing you back to the left. You feel like you're getting squished. That's what those two normal forces more or less are, is the normal force between the person's hand and the book, and the normal force between the wall and the book. And those are in the x-axis. In the y direction, the forces that we have are going to be the force of friction between the wall and the book, and the force of friction between the person's hands and the book. So there you go. That's how you would do a free body diagram of the book. That's all the forces that you would have. Now let's look at the person and realize how Newton's third law comes into play. If we look at the person, now what we can do is essentially figure out how those forces balance. The person we know is going to have a weight acting straight down, shown by Fg, the force of gravity. The person is also touching the floor, so we know that the floor is going to be pushing up on them, and we know that the force of friction is going to prevent them from sliding to the left. In between the person's hands and the book, this is where you see Newton's third law at play. Effectively, what's going to happen is that while the person pushes on the book pushes back on the person. And while the person's hands prevent the book from sliding and push up onto the book is actually trying to push the person's hands down. So when you look at the interaction forces, particularly between the person and the book, you see that those forces are equal and opposite. Now, I want you to practice with this question as well, and then I'm going to go to the board and show you how you would draw a free body diagram for this particular system. Take a minute and draw all of the forces, the normal force, the frictional force, and the weights of the boxes, and isolate each box individually, and I'll show you what answer you should get. Let's look at how to draw the free body diagrams in this particular example for both of our boxes as shown here. Let's look at the box that's flat on the ground first, as this will be a good place to start. One thing you can see that I've done is I've included the dimensions for both of the boxes, and I've also indicated this particular spot right here in orange where the two boxes are contacting. I've drawn them away, so I've isolated the bodies of interest, but I still want to make sure that I capture where they're interacting with each other. I've also indicated my XY axes up here, that'll be important, and I've also included the angle that the box is inclined over here, which is theta equals 30 degrees. Now the first force that I want to draw on the box is going to be the force that acts on all objects on Earth, which is the force of gravity. The weight is going to be acting right in the middle of the box, straight down. The next force that I want to draw is going to be the normal force, which acts straight up. The reason I drew these two right away is because I knew if the weight is acting down, there has to be another force acting back from the Earth that would fight back the weight and keep the box stationary. So those two forces balance out. I know that this could be in equilibrium as a result, so I know I'm good. This could just be how the box is oriented, and it could be good to go. But remember that this box here is touching this box at this particular orange point. So we have to figure out what forces this box here feels as a result of this box leaning on it. Well, you could imagine that if this box is leaning on the other, this box feels that box pushing it. So I'll draw that force in blue. So it feels essentially what I'll call F push. So it feels that box pushing on this. Now again, what we can see is that if this box is going to remain stationary, if there's an X force here, there has to be another X force over here. Otherwise the box would move to the right. So that force is going to be, you guessed it, the force of friction. So now we've got two X forces that can balance out. Now depending on what this question says, sometimes the question can be asked if there's friction between these two boxes, sometimes it might also say there's not, but in this particular case we'll assume that there is friction, and this box here would feel the frictional force of this box pulling it down, essentially. Because if this box did start to slide, it would slide down, and this box would feel that frictional force over here. Now it's important to recognize that this is force of friction 2, whereas this frictional force over here is force of friction 1. They're different, so we don't get that confused. And probably what we want to say also is let's just call this box B and this box A. That way we can do the weight of box B and the normal of box B here as well, just to keep things straight. Now that we've looked at this box, let's go over to this box. What we'd want to do is we'd want to draw the weight of this box acting from its center of mass straight down. Now what's important to realize here is because it's inclined at an angle of 30 degrees, what we could do, if we wanted, is we could incline and just indicate that this angle right there is also theta. That could be helpful later on, but we won't worry about that right now. Now that we've got the weight here, we know we need something to cancel it. We need a normal force to fight back. Where would that normal force be located? Well, it's got to be located at the point where the box is touching the ground. So we're going to have the normal force A pushing back here on this box. That's everything that we have acting on the box, but now let's consider this orange point right here, the point of contact. Remember again, according to Newton's law, that if F push is going this way right here, then F push must be going back in the other direction, over here. And we know that this box here wants to fall to the right and down. So this force here pushes to the left, and we know that the friction force 2 is going to have to point upward here at this orange point to keep this from falling. Now again, if I've got friction going up here, and the weight and the normal force, that can all cancel out, but I've got F push acting on this block to the left. So I need a force to the right to cancel that out. What force is that going to be? Well, that is going to be our force of friction, 3, acting down over there. And that's all that you would do in order to figure out the free body diagram setup for our problem. And pretty much, as you can see, as I've discussed, this is going to help us figure out what we know and what we don't know and how we move forward to solve the problem. Now, we're not going to solve anything right now. I just wanted you to get some practice in visualizing where forces go on a free body diagram and getting used to balancing out forces, so that when you have the weight, you know that a force must be going up to fight it. When you've got F push going to the left, you know that you needed something going to the right. And it allows you to find the forces that you need so that when you do get into the calculations, you know that you've got everything necessary to solve. Okay, this is our last example that we're going to do for free body diagrams. It's actually a really good one. I want you to take a moment and pause your video and draw the free body diagram of the crowbar that's shown below. You can see this bar is essentially jammed in between these pieces of wood and has 3 contact points, A, B, and C. What I want you to do is draw the forces acting on that bar. So take a minute, pause your video, and try and figure that out on your own, and then we'll go over the answer. Okay, hopefully you've had a minute to at least think about it and attempt it. Now here's what the answer would be. Are you surprised? Hopefully not. But remember, normal force is applied by the surface onto the object that's touching it. And the normal force is always going to be perpendicular to the object that is touching it. That's why at points A and B, the normal force is perpendicular to the rod itself. So hopefully this helps you get that concept a little bit more clearly, and this will help you moving forward into other problems. Now what I want to do is introduce an important concept known as 2D equilibrium. Now that we've done free body diagrams, we need to figure out how to apply those free body diagrams, model real-world systems, and then figure out by using the sum of the forces equations how to solve. That's what this class is all about. As I was saying, in ENES 102, statics and mechanics of materials, we assume that every object or system of objects that we're looking at is going to be at rest. So if that's the case, essentially what we're going to be doing is taking the sum of the forces, Newton's second law, F equals ma. And as I said before, we're disregarding the acceleration. The acceleration in ENES 102 is always 0. Woohoo! So, if that's true, the sum of the forces in the x, the y, and the z direction are all going to be 0. So if we were looking at this particular water bottle here, we would see that its weight is acting down. Now if this water bottle was just hanging out in space, it would be falling down, like this. Ooh! That was scary. So, the water bottle needs to have other forces acting on it in order to be at rest. Perhaps there's a force 1 acting down and to the right, and maybe there's another force acting up and to the left to cancel it out. We know that such a force would have to exist, because if we just had F1 and W, the water bottle would be moving. So we need F2. So what we do now in an ENES 102 problem is we sum the forces in all the directions. Here we have a two-dimensional problem. We just see the water bottle on the piece of paper. We don't see a third dimension. Therefore, we're going to use the sum of the forces in the x and the sum of the forces in the y to solve. Our question really is, what are the forces F1 and F2 if we know the theta to be able to solve? If we sum the forces in the x, we would see the following. F1 cosine theta 1 minus F2 cosine theta 2. Unfortunately, that equation is not solvable. We have one equation, but we have two unknowns. As a result, we can't do anything with that. We need to write another equation. That's exactly why we have the sum of the forces in the x, y, and z. Writing the sum of the forces in the y, which would give us F1 sine theta 1 minus F2 sine theta 2 minus mg, this would actually allow us now to solve. Because in a system of equations, when you have two unknowns, but you have two equations, you're in business. You can solve. Now there's all sorts of ways to do this. The most common way is usually substitution. You solve for one variable in terms of the other and plug that back into the equation. But there is an alternative way to do it, and I'll show you that right now. So here is a system of equations that's not really relevant to ENES 102, but you can imagine that it could be. The x and y could be forces or something like that in your problem. So here we have 5x plus 3y equals 59, and we have 3x minus y equals 27. So how could we solve this? We could just do substitution. We could solve the second equation in terms of y, plug that back into the top equation and figure everything out. But the other way you could do it is you could actually look at these two equations, if you have two variables only, and you could multiply the second equation by a factor of 3. What this allows you to do, if you add it to the top equation now, is allows you to get one single equation. In this case, what we end up getting when we add 9x minus 3y equals 81 plus 5x plus 3y equals 59 is we get 14x equals 140. As a result, we can quickly solve that equation and then plug the answer for x, which we get is 10, into the previous question and solve for that. So this is how we use free body diagrams and systems of equations to help ourselves solve static problems and figure out the forces involved in a system that's at rest. Now that we've learned all of this, we're going to finish class or this lecture with a statics riddle, because I know that riddles are fun. So let's check it out. Your final challenge today is a statics riddle. Consider this ladder that we're showing you below that's leaning against a wall and against a floor. Can a ladder stand if there's a rough vertical wall, but the floor is so silky smooth and super clean that there's no friction between it and the feet of the ladder? Draw a free body diagram of the ladder and figure out whether this system could in fact remain at rest. I'll give you a minute to work on it, and then I'll go to the board and show you the answer. Okay, now let's consider this example here with our ladder. Now, when you have a ladder leaning against a wall that is rough and leaning against a floor that is smooth, can this ladder stand? Well, the first step in solving this problem is to draw a free body diagram of our ladder. So the first force we would draw on our ladder would be the weight of the ladder. So we would draw the weight of the ladder as we did in our previous example, going straight down. As you can see right now, if that was the only force we drew on our system, the ladder would not be stable. We need other forces. Let's look down here. What we need to do now is draw a normal force down here to cancel that out, because we know that the floor is going to push back. So we have the normal of the floor. Now we're told down here that mu, for the coefficient of friction, is 0, or that there's no friction on the floor. So the only other spot of contact between the ladder and another object is at the wall. So if we go over to the wall, we can see that the forces we would need to draw here are that the ladder is leaning into the wall, so the ladder would feel the wall pushing back. So we have N wall. And we also are told that there is friction up at the wall. So something we could see is that the ladder would want to slide down. So we would draw a force of friction going upward on this side. I'll say W for the force of friction of the wall. Okay, look at this over for a second. Pause your video and just see, is this the free body diagram you got? And if not, figure out what you did wrong. And before you move on, let's answer the riddle, which is, can this ladder stand? Think about that. Do a sum of the forces and figure that out. And I'll come back to you in just a second and show you the answer. In order to figure out if this ladder is going to stand or not, after drawing our favorite diagram, we need to look at our sum of the forces. If we look at the sum of the forces in the y, we can see that we have force of friction of the wall pointing up minus the weight going down plus normal of the floor going up. How does that look? We've got up, down, up. It's not a cheat code, but that tells us that this is okay. We're good to go because we can have this cancel out. Let's look at our sum of the forces in the x. What forces from our Frey-Better diagram are in the x direction, which, I better put my xy axes on my Frey-Better diagram. The forces in the x are normal of the wall. That's it. What does this mean? We've only got one force acting in the x direction, and there's nothing else to balance it out. If that's the case, what this means is that this ladder is unstable. It's going to fall over, because if the normal of the wall, you can see what's going to basically happen is that when the ladder pushes on the wall pushes back. Then the ladder kind of wants to fall this way, and because the floor has no friction, it can't push back on the ladder, and the ladder will just slide down the wall, even with friction over here. The way to kind of even think about it a little further is if normal of the wall was 0, then the force of friction of the wall is really equal to mu times n of the wall. Well, if n of the wall is 0, well then this whole term is 0. And then the only two forces we have acting on our ladder would be the normal of the floor and W. And I'll show you right now how that's not possible to stand. So now here I've got a ladder, pretty much. It's actually just a white metal rod. And I'll show you how if I incline this and I have only the normal force down here and the weight, what's going to happen. The ladder falls over. This Frey-Better diagram, because we have only one force in the x direction, proves to us that this system is unstable. This is how you use Frey-Better diagrams along with your equations of equilibrium to figure out whether or not your answer and your system make sense. That's the end of our introduction to Frey-Better diagrams and 2D equilibrium. In the next class, what we'll begin to learn is a little bit more about Frey-Better diagrams, and we'll continue to move forward and start to solve more static equilibrium problems, particularly 2D particle equilibrium and 2D rigid body equilibrium. I'll see you next time.